So as we get super close to the end of chapter 9, and therefore super close to the end of all of our BC curriculum, we are going to do one more comparison test to build on the ones that we already have. So this is just to add to your arsenal, just one other tool to have in your toolkit when we're determining the convergence of particular series or not. So the comparison test you've learned before. You have just gone over the integral comparison test. So that's where you are taking a series and you're comparing it to its own integral. So what did its integral do? How does its area behave? And then you can conclude some results about the series behavior connected to the integral behavior. So that was what you worked on in 9.5a. Earlier in chapter 9, we did the ratio comparison test. That's where you compared one term in the series to the next term in the series, where you put the successive term on top and you found the ratio. And if as long as the value of that limit turned out to be less than 1, then we knew that the series itself would converge. If it turned out to be greater than 1, we had divergence. If it was equal to 1, at that point it was inconclusive. So what we're going to do today is add our final comparison test. And this is called the limit comparison test, where we are comparing a series to its own end behavior model, B sub n. So we'll talk about how to find an end behavior model, and then so we can do the comparison. This time, what you're comparing to, the A sub n goes on the top, and the B sub n goes on the bottom. So keep your eye on that. It's different than the ratio test. The ratio test is going to put the A sub n on the bottom with the A sub n plus 1 on the top. But we're comparing not two terms, we're comparing two different series to each other, and we want to put the known series on the end behavior model on the bottom. The key about the end behavior model is something has to be true about B sub n. It needs to have what we call known convergence or divergence. So it needs to have a behavior that you already know. So what we're doing is we're taking A sub n, which is the series we don't know, we're comparing it to B sub n, which is the series we do know. We do know the behavior of B sub n, we don't know the behavior of A sub n. But we've got some conditions, we've gotten used to that. These must be continuous series, they must be positive series, and they must be decreasing. So each term must be getting smaller than the term before. So we have a lot of if-then statements going on. I've listed them, but I kind of want to start with the bottom one. If the limit, all right, so we are going to work out the comparison between the two series, and we'll get a limit value. If that turns out to be between 0 and infinity, so it's not 0, and if it's not infinity, so if it's anything in between, it can't be negative, of course. That should make sense to you. We aren't going to get a negative result because we're not starting with any negative numbers. All of our terms have to be positive in the first place. So negativity is not an option here. But if it turns out to be not 0 or infinity, anything in between, then Series A will do whatever Series B does. So they will have the same behavior in convergence. Okay, so keep in mind that doesn't mean that they will have the same value for convergence, but they will have the same behavior. Okay, so the same kind of, either they'll both converge or they'll both diverge. If we do get infinity, then the only possibility is divergence as a conclusion. You cannot conclude anything about convergence. I'm not saying it doesn't converge. That's not what I'm saying. I'm just saying the only thing we can for sure conclude is divergence. And then finally, if L equals 0, then we can conclude something about convergence, but we can't conclude anything about divergence. So only convergence translates between the two series. All right, so we're making a connection between Series A and Series B. So let's try it. Here's Series A. The series is producing a bunch of fractions. If we take a look at the numerator values of our fractions, these are odd numbers. So we're going 3, 5, 7. The next one would be 9, 11. We're doing the series of odd numbers, and that is produced by a numerator of 2n plus 1. Our denominator, if you recognize those numbers, that is a series of squares. So 4, 9, 16. The next one would be 25. And so we're producing the series of squares. But notice we're not starting with the number 1, so we've shifted these squares over in the series. Same with the odd numbers. We've skipped the first odd number, so we've also shifted the series over, so that's why we have the plus 1. All right, so now we want to think if that is we're calling those fractions, that is our a sub n. So this whole thing is our a sub n series. We want to know, will it diverge or will it converge? So we want to compare to its end behavior model. So that's our first step. We want to find the end behavior model, and we're going to call that b sub n. And so the end behavior model is going to be, what would this look like if we hadn't shifted them around? Okay, if we had no shifts, then, so the shift only just moves it slightly. So what would it look like without the shifts? So the numerator is going to be 2n. That's what it would look like without the shifts. It would just be the series of even numbers that are all still 2 apart, but we're not shifting off of 0. And then the denominator would simply be n squared. That would be our end behavior. Instead of shifting it off 1, we would just have n. Those are called end behavior models. In other words, that means when you're out at infinity, there's really no difference, no negligible difference between the two series. Now this end behavior model can be reduced. Of course, if we have 2n over n squared, that can be 2 over n. So we want to know, what do we know about the divergence of 2 over n? Can we make a conclusion based on anything else that we've already done? All right, well, 2 over n is a type of harmonic series. It's 2 times the quantity 1 over n. So if you can recognize, because of the constant just gets pulled out and it's 1 over n. 1 over n is harmonic, that part of it right there. And we know from previous lesson that the harmonic series always is a divergent series. And so this will diverge. So the key to doing limit comparison is to find an end behavior model and to know what the behavior of that end behavior model is. So then we can do the limit comparison. And so the limit comparison asks us to find the limit as n approaches infinity of the a sub n series divided by the b sub n series. As long as these are continuous, they're continuously positive, and that the terms are decreasing and getting smaller. So we look back at the initial series we were dealing with here. Okay. Yes, these are continuous. We're not going to skip any numbers. Everything's going to proceed. A linear pattern is continuous and a square pattern is continuous. They're all positive, clearly. And they are getting smaller because the denominator they're both growing larger, right? The numerator numbers are growing larger, the denominator numbers are growing larger, but the denominators are going to grow at a larger rate. And so the terms themselves will be getting smaller as the denominator gets larger. So then we can work through just the math of doing our limit comparison. So we'll take 2n plus 1 over the quantity n plus 1 squared in ratio to 2 over n, which is algebraically super awkward. So instead, we will multiply by the reciprocal, n over 2. And then we want to simplify the limit using distributing. So we will have 2n squared plus n in my numerator over 2n squared plus 4n plus 2 in the denominator, which has a result of infinity over infinity, which is indeterminate. So we'll go back to L'Hopital, and that will get us 4n plus 1 over 4n plus 4, which is still infinity over infinity. So one more time to L'Hopital, which is going to give me 4 over 4, which will give me the value of 1. And so we just remember, okay, what we got as a result of our limit, that 1 is between 0 and infinity. So it's not 0 and it's not infinity. So we can conclude that our original series and its end behavior model will share properties. So since series B sub n diverges, then series A sub n will also diverge by comparison. Let's take a look at another example. So here's an exponential model. It's been also shifted, okay? And so we want to take a look at whether or not this series diverges or converges. There are other tests that you could apply to this. And so when you get your choice, you might choose one of the other tests. In fact, you might choose, you might choose the ratio test, or you might choose something else. But we're going to use limit comparison for this. So looking at, we want to find if this is our A sub n, we want to find a B sub n to compare it to. And so the end behavior is going to be 1 over and just 2 to the n. All right, and we just taking off the shift, so the end behavior model is the simplified version without any of the other shifts or translations that have affected A sub n. So now we want to know about the divergence of that. How does it behave? Well, we can rewrite this as 1 over 2 power to the n. And you might recognize that, if you can write it that way, as, oh, that's raised to a power. And so this is a geometric series. And the geometric series has an r value of 1/2. And the r value of 1/2 means convergence for a geometric series. So now we've established that B sub n has a type of behavior that is convergent. So we'll come back and we'll apply the limit comparison. So we want to take our A sub n, which is 1 over 2n minus 1, and compare that to the B sub n, which is 1 over 2 to the n. Again, algebraically, an awkward way to write those fractions. So instead, we'll have 1 over 2 to the n minus 1 times 2 to the n over 1. So that will give me 2 to the n over 2 to the n minus 1. And when I plug infinity in, I will get the indeterminate form infinity over infinity. So we'll apply L'Hopital once more, which will give me 2 to the n times the natural log of 2 over 2 to the n times the natural log of 2, which is 1, which again is not 0, and it's not infinity. Therefore, by the limit comparison, since B sub n has the property of being convergent, then also A sub n is also convergent by comparison. I neglected at the beginning to go through my checklist to double check, is this continuous? And it's an exponential function, so it is. Are they positive? And again, exponential values can't be negative. If you think about what an exponential graph looks like, they're always positive, and we're starting with the number 1, with n being equal to 1 here, so there's no way for this value, these to be positive. And this is decreasing because as the denominator gets increasingly large, then the terms will get increasingly small. So this is a decreasing function. Now, this next slide was previous in your notes, but I wanted to wait to fill it out. I have made a few modifications to this, so you might want to pause the video. You might want to go back into the file in Canvas and pull up the updated file and pull out this particular slide to import it in. Excuse me, because I did make some slight changes to it over the weekend. So I'm just hopeful that this is going to give us a good sense of the big picture of what we've done in Chapter 9. So in terms of the convergent, divergent tests for convergency or divergency, good rule of thumb is just to always start with the nth term test. It's the easiest one to do, but it is limited to only telling us divergency. So if we don't get 0, so non-zero limits are divergent. That is the only conclusion that we can reach after doing the nth term test. Anything else is inconclusive, and it would lead us to, so if we do get 0, or we might get 0, then we have to proceed to the next option. Next one I feel like is always good to look is to recognize, is it a geometric series? And if the answer to that is yes, then if you have r's that are less than 1 and greater than -1, so if the absolute value of r is less than 1, so that's between, those are convergent. And specifically convergent to a sub n over 1 minus r. But if r is not within that limit, in between the constraints of -1 to 1, or if it's equal to, that's inconclusive at that point, and so we would need to move on to the next one. So then we would try the ratio test, and we would check the limit of the comparison of the terms a sub n minus 1 to a sub n. And we would see what we would get with the ratio test. Again, we might get an r, and then it would be, if it was the absolute value of r is less than 1, or between -1 and 1, and those are also convergent. They're not necessarily convergent to anything in particular, unless we're dealing with a geometric algebraic geometric power series, but it only would be convergent in that sense. So then we move on to the more recent test that we've just picked up. We picked up the p-series test, which is the form of 1 over n to the p. And that is going to be dependent on the value of p itself. And so if p is greater than 1, then we have convergency, as opposed to p being less than or equal to 1. P being equal to 1 is harmonic, which is automatically divergent as well. We proved that. Unless we can show that it is alternating harmonic. So then that gets us to the alternating series test. So alternating harmonic is then going to be convergent. So if you have an alternating plus you have a harmonic, then you have a convergent series. Please remember, keep in mind which conditions all of these, so all of them have continuous, many of them have positive requirements with the exception of alternating. Alternating needs to make sure that every other term is changing sign. These need to decrease, but by the time we get down to alternating series, it has to not only decrease, but decrease specifically to 0. That is the condition. If it decreases specifically to 0, not just decreasing to any other number, but has to specifically, the terms must be approaching 0. The last tests that we've picked up have been these other comparison tests. So we've picked up the integral comparison, so you can compare how those turn out. We can also compare the limits of end behavior, which is the one we just did, the limit comparison test. So that's kind of the last ditch, what to do. So those are all the tests we are going to cover in this class. There are other tests to be explored. There are computer programs that are very powerful that will enable you to explore the behavior of other series. But for the purposes of our class, these are the ones that we're going to stick with. All right. So we'll be wrapping up Chapter 9 this week and then be looking at taking the Chapter 9 test. Okay. All right, good. Feel free to swing by. Please let me know if you're having any trouble, have questions you're not able to figure out, because this stuff does get tricky. Use each other as resources, but use me as a resource too. Okay, thanks.